Hello guys, I'm going to do an analytical solution to the Kessler syndrome of maintaining a chain reaction in space or in this for satellites, okay? And I'm going to look at low Earth orbit, and as a little carrot to just continue listening, I'm going to tell you just what my results are, and that is you only need 50 satellites, and then you can maintain a chain reaction. And I'm doing some assumptions here that are simplifying this, because this is like an incredible complicated thing to calculate. So I'm going to calculate it using the birthday paradox, okay? So let's do this. So yeah, only 50 satellites, right? But let me show that to you. So first of all, what is the birthday paradox? It is the surprisingly high probability of two people in a group sharing the same birthday. So most often when people are in a group, they think about, okay, what is the possibility for me to share a birthday with someone else? But in actuality, it is the wrong perspective. The correct perspective is anyone can share anyone's birthday. Okay, so and there is already a formula for this. Okay, so and some background, and I'll quickly explain it. So the idea of the formula that you see there is that you begin with one person and check what is the possibility for that, and the first person can have any birthday, and then the second one cannot have the same birthday. So you do it back. You do it like the opposite way around and check for when there is no match in birthday, and then you subtract that from the probability calculation. So that's the background of this birthday paradox, and I'm going to be able to use this to calculate the chain reaction of satellites. So first of all, I mean there is so these are my inputs. So low Earth orbit satellites, 28,000 kilometers per hour, 90 minutes per orbit around Earth. And I have assumed that there is a 2-year, I mean, if you have a satellite that is, disabled, it will fall to the Earth in 2 years due to the thin atmosphere. So this is an assumption that I've done, and this is something that is valid for low or Earth orbit. Then also a very interesting, very important assumption, because I said that this is very complicated. So the assumption is that every satellite has the same distance from Earth. I mean, they are in the same plane, moving in the spheroid around Earth in that same plane. Or it's not a plane, right? It's a spherical shape of that, and that's an assumption that I did because otherwise it's super impossible. I'm just trying to do this to show that there is even if the satellite is 1 meter in size, one meter, it is a really high probability for collision, even in our the big Earth. When you are in Earth, you think Earth is so big, and this is the idea of the birthday paradox, that no, it's like, no, you can really have the same birthday even if you're not many people. And yeah, so I'll be using that very soon. So let's begin some calculation to be able to do this. The time for the time for the what is it called, for the collision. Okay, I'm calculating the time for the collision. The time for the collision is 0.00128 seconds. Very small because it's so high speed. It's 28,000 kilometers per hour. And I need this. I need to know the part of the orbit and the time, rather the time of the orbit that is the impact. And I'll show you now why. So orbit calculation, part of the orbit that is the impact. And then we take this 0.0128 seconds and divide it by 90 minutes, which is the total orbit. And a satellite meets another satellite's orbit 2 times. And so it's 1 in 21 million. It's a kind of, how would I describe that? Okay, so 1 in 21 million is representing the size of the time where it meets the other orbit. Okay, but we're going to scale this up to n number of satellites. Okay, n number of satellites. And we see here, I call it, I mean, this is valid. Okay, I checked it so many times, but I cannot really call this a possibility. I call it a birthday possibility because it's so weird to explain what this really is. So the birthday possibility for collision between 2 satellites in 2 years, because that's the 2 years comes from this fall through the thin atmosphere. Okay, so this is 1 in 1797. Okay, I mean, it's so hard to explain this. This is what is needed to create a chain reaction. This is the as long as we how to explain this. This is for one satellite. And how it will do during 2 years in this. So you take 21 million, multiply it by 90 minutes, divided by 2 years, and you get this number. Okay, which is going to we're going to put it into the formula of birthday, the birthday paradox. Okay, I promise you this is valid, but maybe it's hard to realize that. But some of you are going to realize that this is valid, what I'm doing, and then you know, okay, so this is the formula for the birthday paradox, and then we simply plug it in, and we get that we only need 50 satellites. And so you could say that maybe you believe that, like, a part of your intuition maybe believes that, okay, I never calculated how 2 satellites happen to be at the same place. What is the possibility for that? But that's the beauty in this, because we interpret the collision as a birthday. Okay, and so we don't need to care about exactly how this happens. It's a birthday, and it is 50 satellites. And I recommend you to go through this many times. Maybe you can look in some Wikipedia or something. But the whole point that the reason why I'm doing this also is because I read that, for example, SpaceX has been approved to shoot up 500 what was it, 500,000 satellites, okay? And what I'm calculating here is an ideal case. It's some kind of simplification, but there's still a validity in this, because if you imagine a collision, when you have two bodies colliding and it's this imperfect collision, it will lose energy, and so you will have the fragments going out of that collision will have different heights in their orbits from Earth, and so it will spread out like that. And so it's interesting also to look at this lowest level. So this is the lowest level closest to Earth, this distance that I talked about. So low Earth orbit, okay? So this is 2 years time to fall down. So if you're even higher, it's like 1,000 years to fall down for a satellite. So this is actually, it actually has some validity in this, and you could see this as you only need 50 satellites to maintain a chain reaction. I mean, or maybe you could say that, okay, it will get 𝗕𝗥𝗦𝗥𝗧𝗛𝗥 in a sense. But the point here is that yeah, what is the point? The point is just to be shocked about the low number here, that, oh, it's only 50. And the point is to realize that the birthday problem highlights the misconception about only looking at one satellite and thinking about how does that do? How does one satellite do? When in fact you should think about all satellites. So, and the result from that kind of thinking is that you get a very low number of how many satellites you actually need. And yeah, so this is my calculation of the Kessler syndrome chain reaction, an analytical solution using the birthday paradox, and only 50 satellites, assuming that they have the same distance from Earth, which is an ideal case, right? But an ideal case is still interesting to think about. And also, even if satellites move in the same direction, their orbits will still cross, and eventually they will cross every orbit very close. So it really doesn't matter that they go in the same direction. It really doesn't matter that yeah, it doesn't matter. Like some people maybe think that, okay, they go in the same direction, the satellites, so those kind of satellites are more safe. But I'm not so sure, because they when they eventually meet, it's going to be many times for many orbits forward, okay? And so yeah, so this is what I say. Okay, so that's it. Bye bye.